Okay. So let's do this. Horsepower rating of the three-phase motor, kilowatt amp rating of the three-phase transformer, about 75% greater for single-phase motors or transformers with a similar size. False on that, fellas. Okay. Y-connected system, the line voltage is lower than the phase voltage by a factor of the square root of 3. False. You guys should have got that one. I gave you the formula. Right? In a Y-connected system, the phase current and line current are the same. True. And the line current of a delta connection is higher than the phase current by a factor of the square root of 3. True on that. The reason for the difference between line current and phase current in a delta connection is that the current flows through different windings at different times in the three-phase circuit. True. Very good. Everybody got that one. Y-connected three-phase alternator supplies a delta-connected resistive load. The alternator has a line voltage of 480. Each resistor of the delta load has an 8 ohm resistance. The load connected directly to the alternator. Therefore, the line voltage is 160 volts. Negative, sir. False. The amount of phase current can now be determined by Ohm's law. Okay, false on that. Connecting the power factor of a three-phase, correcting it, similar to the procedure used to correct the power factor of a single-phase load. True on that. Motor power factor can be computed using that formula. False. We got it on the board. Hopefully we didn't see, yeah, we still saw a few people get it wrong. Inductive Rs in the three-phase can be used using this formula. That was, yeah, that's on the board too, I think, right? Yeah, true on that. One reason why the three-phase power is superior to single-phase power is that in a balanced three-phase system, the conductors need to be only about % of the side of the conductors for a single-phase two-wire system. 75 is the answer on that guy. Y connected, or Y or star. Boy, I told you guys that one was going to be on there, didn't I? Connection is made by connecting that stuff there. This formula, E phase equals E line divided by the square root of 3, is used to compute the voltage on a Y-connected system. Boy, if that one isn't on the board, right? Come on, guys. In a blank connection, line voltage and phase voltage are the same. Delta, good job. In the phase values of voltage and current in a three-phase circuit are known. The apparent power can be used using this formula. Great job following the board on that one. A delta-connected alternator is connected to a Y-connected resistive load. You guys can read the rest on that. 138.57 is the answer there. All right, 17. I'm not going to read that. You guys know the question. 23.1 is the right answer to that using the formula up there. 440 is the next one, 100% on that for you guys. 1.732. That was right up there too, guys. All right. There's the volt amp formula. 1.732 times voltage in the line and current in the line. Everybody got that? Very good. Let's look at these a little closer. Okay. So this first guy here, we got 480 volts right there. We know that's going to be over there on the same as the delta. And in a delta, what do we do with voltage? It's the same, right? Right, there's our answers. Probably tough to see, but on that, most of you guys got this one the second time around. Okay, see the answers there for that one? You guys know what you had or what you didn't have, but there's the answers. Anybody still having any trouble figuring them if I threw one up on the board, or are you all pretty square? I think so. I saw very, very great improvement on the second round. So, all right, here's the answer for the second set there. 240, 20, 34.64 on the alternator, 138, 34, 34 for the load. And then the big one, of course, down here at the bottom, 277, 277, 480, 80, 138, 69, 69, 207, 207. Okay. Extra credit question. What principle do generators operate using? And the correct answer on that was magnetic induction. What's that? Yes, sir. Yes, sir. And then finally, this one should have been almost a gimme. We've talked about it enough. I think I even drew the circle on the board. The voltages of a three-phase system are blank degrees out of phase with each other, 120 degrees. Okay?
Is this the analysis with the reason?
I don't know. I assume it is. Well, I don't think so. Yeah, I think you're right.
It doesn't look like a lot.
No, this is definitely the retest. So definitely the retest. So okay. What? Okay. All right, fellas. Any questions on the test? Everybody feel pretty good about it? Okay. Sorry we had to spend a little extra time on that, but it is important as we move forward for you guys to be able to have a firm grasp on that. So I'm glad we were able to get that thing done this week. Now let's talk about generators. How does that sound? Let me do this. Screen share. Okay. From beginning. Okay, chapter 14. We'll get started with it here today. Slideshow from beginning. Get started with chapter 14. DC generators, fellas. Whoop. This right here, this picture, is a DC generator inside of a drag line. How this guy operates, we have two AC motors. If you touch it this time, we have two AC motors right here hooked up, and that's what's going to generate our mechanical energy. Is these AC motors are hooked up right here with the shaft spinning on both sides. That's going to be what the mechanical energy is to turn all of these DC generators to give us an output. Okay. Story, you can go over there to Wyoming, you're going to see this. I promise you. So, yes, sir. There's a DC motor down there too. But yeah, these are it right here. These are big. This is a big deal here. These are thousands and thousands of amps and volts of DC current and voltage right here. So let's move into it. Our objectives. After studying this unit, we should be able to discuss the theory of operation of DC generators. Okay. List the factors that determine the amount of output voltage produced by a generator. List the three major types of DC generators, and list the different types of armature windings. Describe the difference between the series and shunt field windings. Discuss the operating differences between the different types of generators, and draw schematic diagrams for different types of DC generators. Okay, we'll talk about that moving forward. So, all right, this is something that we need to pay attention to because these are very similar to what we're going to be talking about when we talk about DC motors. This right here is a drawing of what the actual components of the DC generator are. This right here, they call it, this is stator. I'm going to call it a frame. The stator is an AC motor term that they just grabbed for that, but I'm just going to call it a frame. That's typically what I call them, that field. Pole right here, pay attention to where that is, and I'll kind of go through and explain stuff to you in the following slides. Field windings are going to be located inside here in the core. Armature, this big part here, this is the armature winding. I might kill the lights. It's all right if I kill the lights for you, just so you guys can see this a little better. It's kind of, there we go. Yep, you can see it. So right here we have the armature core. The armature core right in here, and then the actual armature windings are out here. And you'll kind of see them a little clearer as we move in. Here's the commutator. I'll explain that to you, and then here are the brushes. We'll talk about those too. Just so you guys get a quick picture of what we're actually talking about, there it is. Okay? Any questions on that? All right. So what is a generator? A generator is a device that converts mechanical energy into electrical energy. Okay? All right. Direct current generators operate on the principle of magnetic induction. Anybody remember what that is? Oh man, we just talked about it a week ago, 2 weeks ago. I'll tell you. We'll talk about it next. Okay, so wire loops connected to slip rings mounted on a shaft with brushing brushes to carry current to the outside load. Loop rotating cuts the magnetic lines of flux and induces a voltage. When a loop is parallel to flux lines, no voltage is induced. And when a loop is perpendicular, you have the peak voltage, okay? So let's see, magnetic induction. Here's the answer to that question. Whenever a conductor cuts through magnetic lines of flux, a voltage is induced on the conductor. Okay, remember that because we're going to do that. I have an AC generator right here. Okay, everybody remember this, guys, from the lab? Remember how we struggled when we stripped the whole wire? Yeah, we did have the non-conducting surface there. Well, this is the Juno that I had to all find out to make this into a generator. No, I didn't have to find out at all, but we're going to show you that in a second. So the polarity of the induced voltage is determined by the polarity of the magnetic field in relation to the direction of movement. Okay. So right here, we have our favorite good old AC wave. And this is maybe not the greatest picture to go along with this, but I'll demonstrate it here in a second on the oscilloscope, is that once we rotate this, once we move north down here to the center, right now we're at zero conduction right here. Our coil is inside of our magnetic field like this when we're right here. And as we start to rotate it, I'm going to go opposite because I put my north on the, oh no, we can go red. As we start to rotate our coil, we start to gain until we're perpendicular, okay? And then once we get to perpendicular, actually this is parallel in the lines, but according to our dots here, we're going to be perpendicular at that point. I got confused on that when I was looking at it, but they proved it to me, so just stick with me on this. So as we're rotating through these lines, our voltage is going up on the wave. We get to here, it's at the peak. It's not going to get any higher when we start to decrease on both this side and this side, as you can see here. And then we come back around, okay? And then this is for an AC wave. Now right here, the commutator, which is going to be this is the commutator, is going to be used to convert an AC voltage produced by the armature to a DC voltage, okay? So I'm going to demonstrate, hopefully, I think right here, on this guy right here, with this right here. I'm going to demonstrate what that actually looks like. So those of us who remember making the motor, we have our magnets up here, our magnetic field. So the opposite, this is actually the opposite of this picture. Instead of rotating the magnet, we're going to rotate the inductor, right? Remember this guy? Coil or inductor? Yeah, we're going to rotate him. So this did work earlier, but please direct your attention to the oscilloscope up here. Right here I have my mechanical energy, right? We're going to change mechanical energy into electrical energy. We got our mechanical energy right here. So when I hook this up to our generator here, we should see an AC sine wave once I start getting it going. Okay. Can everybody see the, we've got some weird stuff happening right now. Can everybody see the screen on the oscilloscope? Okay. So that's not what I'm wanting yet, but it'll start to come on here in just a second. I think that's just picking up me talking. But watch what happens when we start this. We should start seeing the three-way. Technical difficulties. Okay. Stand by. Take that off and in. Good thing I got this spare stuff right here. Oh man, that's really strong. All right, stand by. Sorry for the technical difficulties here. I've been practicing on this thing too much and then tape that up. Okay, now we should start to see an AC sine wave come through. Still not spinning. There we go. Can you see it? Can you see it going up and below? Sorry. Maybe I can get to go with just this. I promise you guys it's working out. Is it working? Yeah, there you go. Okay, that's what I'm trying to demonstrate here, is that just this simple setup here with my magnets and this foil wire, as we're cutting through that, we're actually making a wave. Okay, that's what wasn't great here. We can look at it a little bit harder at the end of class because I did get it going pretty awesome here. It was really good, but I don't want to waste any more time on it right now. But so with that right there, I made this wave. Okay, and this right here is going to be an AC generator because of why? There's a difference between AC and DC, and it has all to do with what, Mike? Changing polarity. Yes, that's one, but let's talk about how it's constructed. Commutator, there it is. Yes, sir. Right here, what we have is slip rings. Okay, slip rings right here. They're not in contact with that the whole time. Okay, you'll never break the contact right there. But with the commutator, we do break contact. Remember that? We talked about that when we were in three-phase, that little guy right there. Anybody got any question with that? Single phase? Okay. We're essentially going to do that right here. So loop is parallel to the line of flux. Here it is right here. Here's an AC generator right here. What I have on my two lights over there, those are slip rings. Okay? All right. And then here it is, the start of that circuit. Okay, when the loop is parallel to flux line, there's no peak voltage induced, and when the loop is perpendicular, we're at peak voltage. So we got a couple of slides here in a row that are just going to kind of walk us through how this is going to generate the voltage here. And this is a DC voltage that we're trying to get out of here. So we're at 0 right there. Then right here, we've come down to this point. We've got the peak of the wave right here. Then once we continue to the next point, that wave is going to go back to 0. Then when we come over here to this side, we're going to go back up the peak because we've cut through all of these lines as we're going up. The peak right there. And then, of course, when we get back to this spot, we're going to be back to 0. Okay, everybody got that? Yeah? Okay, good. All right. So what is a generator continued? Voltage produced in a rotating armature alternates polarity. What we were hoping to have right there, if I could have got my tape to stick on there, was a nice sine wave to kind of indicate that we are going from the positive side back down to the negative side as we cut through these lines of flux right here, as that guy is getting cut through. All right, so DC generators must produce DC instead of AC. Yeah, I think so. When we put a DC generator in, we want DC to come out. So they use a commutator to convert alternating voltage to DC voltage. Commutator is a copper ring split into insulated segments with brushes to carry power to the outside circuit. When a loop is parallel to the flux lines, we have no voltage. Brushes will contact both segments, will be the neutral plane, and a commutator maintains correct polarity to each brush. Polarity voltage stays the same for both halves of the wave. So what does that mean? Let me tell you. Got a little something for you to see here. This gives us an actual visual of what they're talking about. All right.
How do you tackle the power cuts? What common alternative source of electricity? Yes, it's the generator. Let's see how an electric generator works. Electric generator works on the principle of electromagnetic induction and converts mechanical energy into electrical energy.
Yeah.
An electrical generator consists of the following parts: magnet, a rotating coil, conducting brushes, 2 rings, and an axle. The coil ABCD, usually made of copper, is placed between the 2 poles of the permanent magnet. It is rotated inside the magnetic field mechanically by rotating the axle externally. This induces a current in the coil. The 2 ends of the coil are connected to 2 separate rings attached to an axle. The inner sides of the rings are insulated from each other and the axle. 2 conducting stationary brushes, V1 and V2, touch the external conducting edges of the 2 rings. These brushes are generally made of carbon or copper. The axle is rotated to move the coil in such a way that arm AB moves up and arm CB moves down.
Kind of like this, I'm just doing the rotation.
The induced current is generated in these arms.
I believe we talked about Uncle Fleming in the book, right? You guys have that in there? Okay.
The current in the external circuit moves from V1 to V2. After half a rotation, arm CB starts moving up and the arm AB moves down, which changes the direction of induced current. Now the current in the external circuit flows from V2 to V1. Such a current, which changes direction in the circuit after equal intervals of time, is called an alternating current, abbreviated as AC, and the device is called an AC generator. In order to get a unidirectional flow of current, a device called the commutator is used instead of 2 separate rings. A commutator keeps the current flowing in one direction instead of back and forth. In this case, the stationary brushes form contact with opposite parts of the commutator. As the coil turns, it cuts across the magnetic field and current is induced.
Pay attention to this part right here because it's actually going to give us the direction of
The
the
contact of the rotator and the brushes gets reversed. Each brush now touches the opposite segment that it had been touching during the first half turn. By doing so, the brushes keep the current moving in one direction only. Such a device which generates a current that flows in one direction is called a DC generator.
DC generator. Good stuff. Okay. Pretty good graphic there, huh? Gives us a little bit bigger picture of what is actually happening to where, I can't come up here and actually demonstrate it, but that at least gives us the actual motion of what's happening. Okay. All right, so moving on from that, we talked about commutator. This right here, this little guy right down here is called commutator, all right? That's what we're going to that's where the voltage is going to actually be removed from our DC generator and put into our system, all right? Okay? Same thing, it's the same thing, but exactly opposite is what we're going to have, what's going to happen when we change this from a generator into a motor, okay? Which we're going to talk about next after we get done with these. So that's why we put them right next together. Yes, sir. Yep. Yes, there is such thing as a brushless DC motor. Yep. I don't have an example in this one for you, but I'll get one. So when we talk on Monday, you can actually see what it looks like. Yep. Actually, the ECM motor in HVAC is a brushless DC motor. It gets fed in with AC power. It gets translated from AC to DC right inside of there, and it's all contained in that one motor. So they're really neat. Okay, any other questions? Okay, so right here are two actual images of commutators. This right here is off of that DC generator in the right line right here. These little spots right here, where these are the brushes right in here. Right here where you see the top of the wires, these are called pigtails. Brushes are stuck in here. This little thing right here is called the brush box. And those are sprung. We got a spring on there to hold them down on top of this conducting circuit. So you can see in here, this thing has got a bunch of little lines through it. That's in order to only allow that certain amount of space to conduct. Okay? And what's in between here, that white stuff in there is called mica. It's like an insulator. Right? And then this one is one that's actually working in the machine right now. Here's one just one that right on the back of the yard as well. So see the difference. That's the nice shiny part right here. But this commutator is hooked into the big thing right? It's called what? We rotate in the center. It's right on your tip of your tongue, armature. It's hooked on the armature. The armature is the big rotating thing in the center. Okay. On an AC, that's called the rotor. On a DC, it's called the armature. Okay. Okay, so here we go. We got the good old DC wave right there. The loop completes one rotation. That's what that output's going to look like. Okay, guys? Right there, two nice little lines. Now, what happens if we want to make this? If we have a load that's on this, and we're going to see a definite slowdown in that load in the frequency when we get to the off-peak side of this hump until we start charging that function. So the way we get away from that and stop causing that happen is we just skip forward the slide if we're ready, and we add more coils like that. Okay, that's going to increase the output voltage, and we can even add. I think here's your DC motor design right here. Yeah, how you have everything in there. That's what the output that we're going to get when we add two separate coils, on this, and they're both traveling through that magnetic field at the same speed. We're going to get a nice, even DC wave. What this will look like if we were to have our electrical eyeballs in here, what we can see when we're reading this on our meters, we can see a nice DC signal right there. We wouldn't even really notice these humps when we come down here. It would just be a nice DC wave just right at the top. It looks something like this. That's where the actual working voltage is going to be. Remember, RMS, root mean square. This right here isn't where the working voltage is. It's 707% of that. That's going to be basically what we have right here at the top. It's going to be our working voltage right there, just right below the peak. Yes, sir. Oh, yeah. Yeah, so we're talking generator. When we talk about the big generator, I'll get to a spot on here where we actually see the actual size of the armature, the actual lines that are going to cut the flux lines, and yes, it will be, this will be, the waves will be much more packed together, and it will be almost like, it's not even there's an AC wave happening at all. It'll just look like a straight line. Because it's happening so fast. Okay. All right, so what is a generator continued? Rectified DC voltage. Who knows what rectified means? Yes, sir. I'm surprised. Very good, Mike. Yes, sir. I got it highlighted there because I wanted to do this and read you the direction or the definition. Electricity to change alternating current into direct current. Okay, that's what rectified means. Top words for toilet. No, we don't want to know that. Get off of me. Okay. Rectified DC voltage pulsates turns on and off, but never reverses polarity. Polarity for each brush remains constant. The output voltage is DC. Increase of the output voltage by increasing the number of turns of wire in each loop. So we'll see that here in a second too, hopefully, if I got this set up right. But the loops are connected in series, so voltage adds. Multiple loops increase the average voltage to reduce the pulsation. So there's your question right there. We're adding multiple loops, so we're going to increase the average voltage and decrease that ripple that we would have with just the two humps right there. So when we get in here a little deeper, hopefully, oh, one more slide, I think. Okay, what is the generator continued? The loops are placed in slots for slots of the conductive iron core. That's going to be, the conductive iron core is going to be our armature. Okay, and this provides a low reluctance. I have reluctance highlighted there. What does reluctance mean? Not Michael. Somebody other than Michael. Booyah. Thanks, sir. Excellent. That's page 10 right here in our book, right?
He pretty much read the exact definition right off the page in his manual. Reluctance is a resistance to magnetism.
Okay? So by adding all of these loops, we're going to provide a low reluctance. So we want it to get magnetized. Okay? A low reluctance path for magnetic lines plus increasing the loop inductance and providing a higher induced voltage. Okay? Armature assembly of the iron core is the commutator and the windings. There's three basic types of armature windings: the lap winding, the wave winding, and the frog winding. So lap is going to be series, wave is going to be parallel windings, and draw leg is going to be series and parallel. Okay. Two in series, but they're all going to be parallel. Okay, here's what I was looking for. So, story. Here is a picture of the question that you asked. The slats here is essentially another loop that's going to go over to the back side of the cylinder here, which this is an actual armature right here. This is armature pull out of the frame, and it's getting rebuilt. This is the commutator itself. It's nice and plugged up in the shop. So yes, each one of these little paths right here is a coil. Here's the end of the wire right here. Big, huge chunk of wire right there in that inductor. But as this thing gets, we get this motor moving, we're going to be making a real nice solid DC sine wave, or DC wave, just a straight solid DC. All right, so here is an armature without the loops. Okay. So that whole space right here is going to get filled completely with wire. Little thin strips of wire. So through that, each one of those things, we're going to have a nice packed, tight loop wire. And so it's going to actually come out to be the same height as this iron core slats here. And then once we get done with those wires, we're going to take the end of each one of them. So this coil is going to have a beginning, it's going to have an end, and we're going to hook it in right here on one of these little slots inside of this commutator. Right here are little slots. Right here, right here, right here. So each one of these, go back up there. Each one of these guys is going to conduct at a very certain point as this rotates. Okay? When this guy right here makes a connection with the brush, that's the only point on this whole thing that's going to conduct, because each one of these are insulated from each other. Okay? So how many closing out arms just the same amount or twice as many? So this doesn't have any coils on it. Right. So what's going to happen is on the opposite side of this circle. Let me just draw it up here real quick. So we have a coil of wires that's going to start here, and then it's going to go off and get wrapped around here, and then it's going to come back, and it's going to get landed over here. Right.
So in those two spots, will they be on that's where it uses the voltage?
Yep, so on this, yes, the induced voltage is going to come out for that particular loop is going to come out right here. Yep, and obviously there's about 100 of them motors on there that are just going to go like this. So at every single point, basically, and how a brush works is a brush is usually going to, depending on the size, but most of the ones that I've seen, the brush is going to get set up to be able to conduct on 3 of these little lines. That's what our goal was, to get the brush to come and make contact with 3 of these little lines at a time. So we were increasing the amount of loops even more by adding that bigger space that we can conduct. Because, man, once these things get going, these go about 1,200 RPMs when they're really swinging, and you can't even see these lines in there. It's just really moving fast. So we add these brushes in here to give that conduction space a little bit greater amount of time to conduct between here instead of just right here. You know what I'm saying? Okay. All right. Any other questions about the armature? Some of these, so these motors right here, the guy that actually invented the design on these, I worked with when I was working with Joy Global. He's crazy. His name's Dave Wendt. He's like a super genius. It's hard to even talk to him. All of these, the principle on these are all the same on DC motors, but you can very easily manipulate how they react by just the amount of coils that you use, how they're wound. So you can get a lot of different kind of voltage and current production just on how you handle your inductors inside of here, even how you wind the wires around the core. Okay, moving on. Okay, so I think I said these backwards, didn't I? I think I said lap winding was in series and wave winding was in parallel. I'm a big fat liar. Lap armatures have their windings in the parallel. They're using machines intended for high current and low voltage operations. So these guys are going to be like real heavy loads. Like one specific example I have that I can show you a picture of is they have a big, huge elevator going in and out of Homestake Mine. It's a man elevator. They take a lot of equipment down that get down through it, but it doesn't need to be a high speed. It needs to be able to haul a huge load up and down the grade of the mine shaft. Okay, up in Homestake in the hills there. So wave wound armature. A wave wound armature have their windings connected in series. Wave windings are used in machines intended for high voltage and low current operations. So when we're talking DC, okay, this isn't the same in AC, but when we're talking DC, we have different things doing different things. So when we're talking torque, so how strong the motor can spin or what the amount of load that it can pull, we're talking current. Okay, so T-O-R-Q-U-E, right? Torque equals current. Torque equals current, okay? So when we're talking speed, we're talking voltage. So speed equals voltage. That's going to be the same in any kind of DC stuff that you get into. Voltage equals speed. And that's why this is kind of older technology, because this is just how simple it is right here. Now, when we were talking AC motor, how do we increase the speed on an AC motor? Yes, sir. Frequency. I don't know if that's spelled right. I don't say. And that's what we did in VFD. So if we just plug a motor in, a regular old AC motor into the wall, how fast is it going to spin? 60 cycles a second. Yes, sir. Yes, sir. 60 hertz a second. So that's kind of where this all is coming from. The DC technology has been around a lot easier. It's a lot easier to manipulate the voltage on the DC circuit. So if we need a motor that can spin a lot faster than 60 hertz a second, before we invented VFDs, we had to just figure out a DC power supply, and then we can increase the speed of a DC by just turning the, especially when we're talking generator here, we can increase the speed of a DC generator just by making it spin faster. Just increase the RPM of whatever's driving it. Okay? Got a little sidetrack there, but it is kind of nice to be able to see the difference here. Also, in an AC, torque is current. We'll sneeze there. Okay. Any questions about armatures? I think we're going to look at an armature right here. Yep. Okay, so right here, obviously, damn it, I can't see that.
Obviously, right there, we have the iron core, and then the windings going around the iron core in the circular motion. And they're going to be tied in right there with the commutator.
Okay. Frog legs. I've never heard of the frog leg winding until today. I would think that in my world, that would just be the series parallel. So frog legs on armatures are connected to series parallel with windings for demonstration machines intended for reading voltage and current application. So we have three different styles here. We have the we have the lap wound, which is for high torque, low voltage. We have the wave wound, which is for low voltage, high torque. And then we have the frog leg, which is right there in the middle. We have a little bit of mix of both. I will pay attention to that. Okay? I will pay attention to that. All right. Little subtle hint there for you. Okay. Here we are again looking at armatures. Any question about them? Okay, brushes. I wish I had one. Actually, stand by.
Seems like I'm missing one over here. Seems like I'm on the phone.
Brush is what we're going to use to connect the wiring, the output wiring that we're going to get on our generator to the actual commutator. It's going to be able to drive on the pump, and that's what's going to give us our voltage output that we're generating. Maybe I'll move that wire so you can see brush. I don't have a good picture of one for you, but it's not consistent inside the brush. I'll get one. I should have some oil in mind. Sorry, very nice brush. Okay. But anyways, those are they're just little carbon rectangles here. They look like this. They got two wires coming off here that you bring up. The wires just go in here and here, and these are usually made of graphite or some sort of a carbon that's conductive. So these are going to be shaped like this, to where as that circular commutator rolls through here, these are going to be able to make contact with those three spots I was telling you about. Three separate spots. Okay? That's what a brush is right here. This is a brush. And I think I got some stuff here. So brushes ride against the commutator segments and connect the armature to the external circuit. All right. So as that thing is rotating and we're generating that voltage from having that induction happen around the outside or for what's called the frame, the brushes is what's taking that rotational energy and putting it out onto our wires to give us the energy that we run to whatever load we're trying to power. So the brush or armature leads are labeled A1 or A2. So we got an in and an out, A1 and A2. All right. Made of softer material than the commutator. Usually, like you could, if you wanted to, you could probably. They're very hard, but you could probably write your name with them on a piece of paper because I think they're made of graphite. So. Okay, here is the actual brush riding on top of here. So these guys, right here, there's the actual brush itself. It's just a black carbon rectangular disc that rides on this rectangular rectangle. This rides right on these commutator rods here. So here's the pigtails that come off, and these are actually going to go up and they're going to land on this, where these wires go to right here. See these big wires right here? These are armature cables. These are going to land on each one of these brush boxes, and then the pigtails of these brushes are going to land on that same common point on the brush box. So the brush rides inside this, which is called what? Brush box. This is called a brush box, okay? This is the spring that holds the brush down, because over time, what will start to happen is as this thing rotates 100,000 times a day, it will start to get an egg shape. Nothing, I mean, man made this, okay? Well, man did, not a higher power. So over time, like any machine that man made, it's going to wear out, okay? And that spring tension that's inside the brush box here, holding this down with a spring. Here's my spring. Good spring, right? It's holding this down, so as this thing rotates and it's out around, as it gets to this shallow part right here, that spring is going to push that brush down on top of that shallow spot. Yes, sir. Graphite. So they're very hard, but these are a thing that you have to check on. They do wear out. These are getting pushed down all the way, and as this, you know, when you look at this here, this is all very smooth. Like we'll look at it if you touch them. Actually, they have a brush right down there. It's a silly name. We'll look at it in the lab. Yeah. That's an alternate piece of thing. I'll start. Yeah, sorry. Okay. Yep. But yes, so yes, they are very hard. And there is an industry that is specifically designed to make those. There's several different manufacturers, asphalt, carbon, several different pieces of brush manufacturers, and they all have a little bit different chemical makeup of what each of those individual brushes are. But they're like, just imagine in your head that you took some pencil lead out of your pencil and put it in the rectangle. It's not very bendable, it's very brittle, so they chip real easy. So yeah, I mean they'll check those, see one in the left. So any other questions on brushes? So pigtails. Pigtails come up and they hook in here to the actual armature, and this is where we transfer the rotational magnetic energy from the armature and the commutator into the DC voltage output to supply our system. Okay. Pole pieces, and then we're going to be done for the day. So the pole pieces, right here, this is a pole. Right? Pole pieces, right here. These are located inside the housing of the DC machine. When we say DC machine, we're talking about motor. Okay? It's a motor, or excuse me, a motor or generator, but something that's mechanical. Located inside the housing of the DC machine, provide the magnetic field. So, okay, Brian, great. We've got this rotating shaft inside here. If it doesn't have any magnetics, it's just a rotating shaft. It isn't doing us any good drawing mechanical energy. We have to be able to give that magnetic field, and these pole pieces are what does that. Okay. Those are these right here. Those are the magnets around that armature. Okay. So, made of good conductive material like soft iron and steel, yes sir. Some called magnetos use a permanent magnet rather than an electromagnet. Right here, which could be considered a magneto. Okay, permanent magnets right there. All right, and that's where we're going to leave off for today. I think we are, let me look here. Yeah, we're done with, we ran out of our time. Hang on for just a minute though, please. Let me make sure that we at least got dang near halfway through. I think we did. Oh yeah, we're more than halfway through. Brushes, yes sir. Okay, that's a great spot to stop. We're at 29 to 49. I'll get a brushless DC in here, and then we'll pick right up there on Monday. So those of us, let's see, Phil's not here. There's only just a couple of us who didn't get our review questions done. I would love to be able to go through those. And I think I'm just going to make the executive